Hey guys, today we're going to talk about regression, which is also known as calculating our line of best fit, or our LSRL, which is the least squares regression line. Remember, when we're taking a look at data that's bivariate, we looked at scatter plots last class and our correlation coefficient that measured the strength of that linear relationship. Well, today we're going to take this bivariate data and we're going to create a prediction equation or a line of best fit. When we have data with both x and y values, our x variable is our independent variable, also known as the input. Our y variable is the dependent variable, also known as the output. In statistics, our x variable is called the explanatory variable, because typically we think of it as explaining the outcome or explaining the response variable, which is our y variable. So when we look at y, we say y depends on x when we were in Algebra 1. In statistics, we say y responds to changes in x. So as we change the input, we're looking at the response variable or the output, and that's what we're measuring. Well, for our purposes, we use the input to predict the output. We use our x values to predict our y values. And we do this by creating a linear equation. Instead of y equals mx plus b, what you'll often see in statistics is y hat equals a plus bx. The little up arrow above the y is pronounced y hat, and it means predicted y. It's really important that you don't forget to put the hat on the y. If I have a y value, that represents an actual point, an observation. If I have a y hat value, it is the predicted y value for that input or that value of x. So it's really critical you remember to put the hat. When we're writing our regression equation, remember the coefficient in front of x along with the sign is the slope of the line. The slope of the line is the approximate amount by which our y increases or decreases, if it's negative, when our x value increases by 1 unit. We'll talk more about that later in this video. Our constant is also known as our y-intercept. Our y-intercept is the y value when x is 0, or it's the approximate height of the line when x is 0. In some situations, our y-intercept has no real-world meaning, and in other contexts, it does. We've just got to look at each situation separately. When we're writing a regression equation, we are concerned with the line of best fit. That was just a term we used in Algebra 1. More specifically, the line of best fit is the line that gives us the least squared residuals, or it's the least squares regression line. It is the best fit to the data set, and it's the line that minimizes the sum of the squares of the deviations between the line and the data point. It's going to make a little more sense if we actually look at this with a picture. So here is a scatter plot, really simplified with 3 data points. We are going to look at a line that could best describe on average those data points, or a y hat or prediction equation. And now we're going to verify whether or not it is the line of best fit. Now, we just made up this equation. Remember, your line of best fit typically goes through the middle of your data points. It does not have to go through all, or in this case, any of your points. It is our on average best prediction for y for a given input value of x. So we're actually going to go through and we're going to calculate what we call the residuals, or the errors, or the deviations. In other words, I want to know how far off my actual point and my predicted y value are. So when we calculate residuals or errors, it is our actual value minus our predicted value. So over here, my actual y value is 0. I want to calculate what our y hat or our predicted y value would be. To calculate this, I plug into my equation. Y hat is 0.5 times x, which is 0, plus 4. So my predicted y value is 4. Now I need to look at this distance here. This is known as my residual or my error. How far off are my actual and my predicted values? To calculate this, we take our actual minus our predicted, 0 minus 4. I have an error or a residual of -4. I'm going to duplicate the calculation for all of the points in my scatter plot. So here, if I was looking at my predicted y value for an input of 3, I would get a predicted y value of 5.5. Actual minus predicted gives me a positive 4.5 for a residual. Here, if I were looking for the predicted y value when x is 6, I would get a predicted y value, y hat, of 7. Actual minus predicted gives me a residual of -5. Now we sum the squared residuals. So we take each residual, square it, which makes it positive, and we add up the sum of all of the squared residuals. 16 plus 4.5 squared plus 25 comes out to 61.25. If there's a better line of fit, it will have a smaller squared residual. So we're going to take a look at another example here. Notice this is a new line of fit, and we're actually going to calculate the residuals for this line of fit too. Now would be a good time to pause your video, calculate all of your residuals, your actual minus predicted y values for each of these x points, and come back to the video and double check your work. You should have gotten a residual of -3, +6, and -3. If I square the residuals and add them up, I would get a sum of my squared residuals of 54. Well, that's obviously a lot smaller than the other line we looked at, so this is a better fit line. Now, how will I be able to determine if it truly is the line of best fit? Well, first and foremost, the line of best fit, the sum of the residuals, before I square them, the sum of the residuals will always be 0. It's because my line of best fit should go through the middle of the data, so I have the same total sum of positive residuals and negative residuals, or the same amount of deviation above the line of best fit and below the line of best fit. Now, our calculator is going to do all the work for us, but our line of best fit is going to be the line that has the overall minimum for the sum of the squared deviations from the line, and that's our LSRL. We're going to calculate on our calculator our least squares regression line or our line of best fit. When we do, we're going to need to make sure that we can interpret in the context of the problem the slope and the y-intercept if it has a meaning, and then also take a look at the correlation coefficient that we discussed last class. When we look at slope, we're looking at a ratio. Remember, change in y over change in x. For every unit increase in y, the slope represents an approximate increase or decrease. Increase if it's a positive slope, decrease if it's a negative slope, of the slope value in y. Now, it's going to make a lot more sense when we work a problem, but make sure that we understand this is an approximation. Not every point in my scatter plot follows the line of best fit exactly, so I need to make sure I include that word. From last class, you'll recall our correlation coefficient R represents the strength, the direction of the linear relationship between x and y. So let's take a look at some data. We have x values and y values that represent the age and heights of 7 children. Now it makes sense if we think about this, that height of a child would depend on the age of the child. So that means our height were our y values and our age were our x values. We are going to find the least squares regression line using our calculator. Then we're going to interpret the slope and the correlation coefficient in the context of the problem. So going to your graphing calculator, we're going to enter those data points in list and spreadsheets. Next, you're going to add a page, and we're going to add a normal calculator page. We're then going to click on Menu, and since this class is called Statistics, we are going to select Statistics. There we are, sorry. And this is going to be a stat calculation, and we're going to do linear regression A plus BX. We will tell our calculator what our X values were. I called my X list X. My Y list was variable Y, and then we can tab all the way down or toggle down to OK. If you notice, the first line or the second line here says regression equation A plus BX. That gives me the format for my equation. My A value is given, which is my y-intercept. My B value is given, which is my slope. And if I go down here, I can see my R value, which is my correlation coefficient. So we now have our regression equation. Y hat, make sure you put the hat, this is the predicted Y, is 0.342x plus 20.4036. We could also write this as 20.4036 plus 0.342x. If we write our regression equation with x and y, we have to make sure somewhere in the problem we've defined x as the age in months of children and y hat as our predicted heights of those children. The other thing that you will sometimes see is people combine both of those. If y represents height, we'll write height hat equals 0.342 x represented age plus 20.4036. Now let's take a minute to interpret what that slope and that correlation coefficient mean in the context of the problem. First is our correlation coefficient, 0.99. That means there is a strong, this is a positive number, positive, linear relationship in context between the age and the heights of children. Now taking a look at slope. Our slope was 0.34 or 342 over 1. Our y units were the height of children in inches, and our x units were the age of children in months. That means for an increase of an age of 1 month, there is an approximate increase of 0.34 inches in heights of children. Make sure we understand this is not exact, but is a prediction. We could also write that same slope as 3.42 over 10. So we would expect, on average, an approximate increase of 0.342 inches for a child for every extra 10 months of age. So as long as we're using an equivalent value, we can interpret slope. It can be a reduced fraction or a non-reduced fraction. Now we're going to use that prediction equation. Y hat is 0.342x plus 20.4036, and we're going to predict the height of a child who is 4.5 years old. Be careful here. All of these ages were in months. So we would need to convert 4.5 years old. 4 years old is 12 months a year, 48 months old. Half the year is another 6 months, so that child is 54 months old. We would use our prediction equation, plugging in our x value for months and calculating our output. In this case, we're using x to predict y. Our y hat, or our predicted y value, is 38.8716 inches, or just above 3 feet. Let's do the same thing for predicting somebody who is 20 years old. 20 years old is 240 months old. There are 12 months in a year. So y hat is 0.342 times months, because those are the units of our input, plus 20.4036. Our y hat value comes out to 102.484 inches. Well, if that sounds like a big number, divide it by 12, and that means we have an approximate height of 8.5 feet. On average, I don't believe 20-year-old individuals are 8.5 feet tall. So there's clearly a problem with using this equation to predict the age of somebody who is 240 months old. The reason for that is if you look at the input data we had for X, this equation is based on X values between 16 months and 120 months old. 240 months old is well beyond the scope of this study that we used to create the line of best fit. We should not use our equation to predict for X values that are beyond the scope of what we've looked at. That's called extrapolation. When we have a least squares regression line, we should not use it to predict Y for values of X outside of the data set. We simply do not know whether the pattern we've observed to calculate our regression equation continues for X values outside of this range. It is a common mistake people who do not know statistics makes. Please don't make that same mistake. Now, remember the equation that you've calculated thus far. This equation was actually using an input of age to calculate an output of height. So we used X to predict Y, or we used age to predict height. Can we use the same equation to go backwards? Can we use height to predict age? I would recommend that you create the new equation and see if it's the same. And to do that, we just go back to our calculator. But now when we select our regression equation on our calculator, we switch our inputs and our outputs. We switch X and Y, and we'll notice that we get a brand new regression equation. Remember, your R value does not matter what you call your input and your output. However, your regression equation is very different. This is the equation that I would use if I wanted to input height and get an output of age. It might be more helpful to write this as age hat equals 2.889 times height minus 58.198. Be careful. Make sure you're only inputting the input to predict the output. This is the equation that we would use to predict Y from X, or to predict height given a person's age as the input. The second equation is what we would use to predict age from their height. If you want to switch your input and output, you need to calculate your new regression equation to do so. Now let's take a look at the same data and let's calculate our X bar and our Y bar, so the average of X and the average of Y. There's a really easy way to make your calculator do all this at once. When we go back to our calculator page, we are going to go to our normal calculator page. We are going to go to our menu. We're going to pick Statistics and Stat Calculations, and now we're going to select two variable statistics. We're going to tell the calculator where to pick our X values and where to pick our Y values. And then when we click OK, you'll have to scroll, but your calculator finds anything you want to know about X and Y. The mean, the standard deviation, the 5-number summary for both X and Y. So you want your X bar value and you want your average Y value. We found our X bar and our Y bar. Our X bar is 62.7143 and our Y bar is 41.8571. These points are always part of my least squares regression line, guaranteed. In fact, let's take a look at a scatter plot. When we add a data and statistics page, it looks like there is a very strong positive linear relationship between X and Y. We can actually go Menu, Analyze the graph, and have the calculator show the regression equation. The only thing missing is the hat. And every single time I get a regression equation, along this regression equation, I will always be able to find my X bar, Y bar point. My average X, average Y is always a point on my least squares regression equation. Well, that means something to us in terms of resistance. We know that our correlation coefficient was based in part on the calculation of x bar and y bar. Now we know that our x bar and y bar point is always on our least squares regression line. That means both our R value and our line of best fit are non-resistant measures. They are not resistant to outliers. In other words, they are greatly impacted by outliers. Now, on your AP Statistics formula chart, you have a number of equations that you will find on your formula chart dealing with regression. Now, if you look at your y hat or predicted y equation here, they've changed the symbol. B1 is the coefficient in front of x, so B1 is your slope, so you have two equations that you can use to calculate slope. B0 is actually your y-intercept, and you have one equation that you can use to calculate a y-intercept. If we take this equation, where we're really getting this from is we said on our regression equation, if we know that x bar, y bar is always a point, we can simply do a little bit of algebra and find that y bar minus b1 x bar is our y-intercept. We could rewrite that and we could get this format too. So that's simply a little bit of algebra. If I get computer data, it might be important that I can use these formulas to calculate my regression equation. Here's an example. If you notice, we have data here on the speed limit that's posted and the number of accidents on average. Accidents depend on the speed limit. Accidents are our y and speed is our x. We're going to calculate the least squares regression line. So we need y hat equals BO plus B1x. First things first, we need to calculate slope. Well, I know that I have the standard deviation of x and y and my R value. So one of the formulas on my formula set chart said R times standard deviation of y divided by standard deviation of x. So our R value is 0.9981, standard deviation of y divided by standard deviation of x. And our slope comes out to 0.723. If I now use my equation for my y-intercept, B aught is y bar minus b1 x bar, I can calculate my y-intercept using the slope that we just calculated and my x bar, y bar, my average x and y values that were given. My y-intercept is negative 10.9105. So if we put that together, our regression equation is negative 10.9105 plus 0.723x. We certainly can rewrite this as 0.723x minus 10.9105. Or if we don't want to have to define x and y, we could write this in terms of the variables. Accidents hat equals 0.723 times speed minus 10.9105. We can use that equation to find the predicted number of accidents at any speed. All we have to do is plug in the speed. Now, depending on what stat program you use, whether it's SAS or R or JUMP, any of our programs that we use for computers are going to have slightly different outputs. This is another example of a computer output. This example is based on a scatter plot where percent of body fat was our Y variable and our X variable was waist size in inches. If you look, you have two lines of data, a line for your constant, so everything on this line is dealing with my constant. In fact, this column is the coefficient for the constant, and a line that deals with your waist. This number right here is the coefficient in front of my waist. Well, remember, my waist size was x. The coefficient in front of x is my slope. The constant is my y-intercept. So y hat equals my slope times x minus my y-intercept. Or I could write this as percent body fat hat equals 1.70 times my waist size minus 42.734. Once we have our regression equation, we can use it to calculate different values or even to interpret. The slope was 1.70, which is the same as 1.70 over 1. Remember, our y units are percent body fat, and our x units are inches of our waist size. So we can say, for an increase of 1 inch in waist size, there is an approximate, it's positive, so increase of 1.7% body fat. Another way of saying that is, on average, you increase 1.7% body fat for every increase of 1 inch in waist circumference. Last but not least, we can use this data to calculate our R value. Well, nowhere in this computer output do I have R, but I do have R squared. And we know that R is the square root of R squared. We can take the square root, but to do so, we must first convert our R squared value to a decimal. So this is the square root of 0.678. Remember, when you take a square root, you have a positive square root and a negative. The way you know which one to use is your R value has the same sign as your slope. My slope is positive, plus this problem told me I had a positive association. So I will have a positive square root, which is 0.823. So if we were going to interpret that, we would say there is a strong positive linear association between waist size and percentage of body fat. Now that we've taken a look at our least squares regression line, there are important things to remember. Remember that your x bar, y bar value is always part of your least squares regression line. Remember, that means that your least squares regression line is not resistant to outliers. In fact, we'll learn next class how greatly impacted it can be by outliers. The sum of the residuals for our least squares regression line will always be 0. And when we square those residuals and sum them up, our line of best fit will have the absolute minimum least squares regression line. All right, guys, thanks for watching.